Hey guys, just quickly want to go through a review of some of the gravity stuff. I know it says gravity and circular motion, but it's pretty much all gravity stuff. So, the circular motion stuff we've already kind of covered. It just means this kind of connecting the two things. So I'm just going to kind of go through this review sheet. I'll attach the actual document for you as well. But just go through each of these answers, kind of fill it out as we go along. Probably the only assessment will be a really simple quizzes by the end of the week. I think that should be about it. I'll keep it pretty short, just because I want to be, I'll give you a lot of work in this last week, and you guys can enjoy the time off for spring break. Okay, so the first question says, how is centripetal acceleration related to the acceleration of gravity for an object, for an orbiting object? And the answer there is quite simply that they're the same thing. Sorry about that. That was my daughter laughing at me in the other room, sitting here talking to myself. But yeah, they're the same thing. So the acceleration of gravity is the centripetal acceleration for an orbiting object. Remember, an orbiting object is just an object in circular motion. So you could just say a centripetal acceleration is equal to g for an orbiting object. Subscript. There we go. So that's all we mean by that, is that for orbiting objects, centripetal acceleration is equal to the acceleration of gravity at that altitude, which means that since small letter g changes with altitude, that means that the higher and higher the radius of the circular motion, the less and less centripetal acceleration is required, which we already know is the case from our last section on circular motion. Kind of same idea on number 2 here. How is centripetal force related to the force of gravity for an object? They're the same thing. Again, Fc is equal to Fg. Not big G, F subscript G. They are the same thing. The force of gravity is what provides the centripetal force necessary for that circular motion. Number 3, what has to happen in order for a satellite to orbit? On some type of assessment, I would give you this question worded a little bit better. But basically, I'm just saying, you can't just take an object up into space and it just magically orbits. It has to be given a really high tangential speed. If this were astronomy class, I might say really fast sideways speed, a speed that is directed kind of parallel to the surface of the Earth. Okay, so we need to launch it up. We do need to get it above the atmosphere so that there's no friction, but we need to get it going really, really, really fast so that it falls around the Earth rather than into it. Now, remember, objects don't just magically float when they're placed up in outer space. They have to have a really, really high tangential speed, and that's how orbits happen. The International Space Station has a tangential speed of about 17,000 miles per hour. So when we send up astronauts up there with a space shuttle or what have you, they get up there and they have to get up to that speed. Just hey, get above the atmosphere and then magically float there. That's not how that happens. Okay, orbits does not mean floating. Orbit means falling. It's a continuous free fall around the Earth rather than into the Earth. Okay, so given a high tangential speed, some kind of secondary answer to that is that you have to be above the atmosphere. And the only reason that you have to be above the atmosphere is to avoid friction. A couple terminology questions here. What does orbital period mean? Orbital period, we usually indicate that with a capital letter T. That's just the symbol for it. But that means that T, period, T like time, period like time period, that means the time to complete a full orbit. So time to complete a full circle or a full ellipse, for say the Earth as a satellite around the sun, our orbital period would be 365 days. The orbital period for the International Space Station is about 90 minutes. So it completes about 18 orbits a day at that rate, right? So that's what orbital period means. And remember, orbital period would increase with distance, with radius. Which takes us to our next question, is what does orbital radius mean? That just means the center to center distance. I just say center to center because people think it's surface to surface and they make it more complicated than they need to. But the center distance between the center object, we'll say in both cases we usually talk about Earth, and the orbiting object, a satellite. That satellite could be the moon, or a man-made satellite, could be the International Space Station, or that center object could be the sun and the Earth. You know, whatever the center, whatever the large object is, and whatever the small object is. It's just the distance between them. And usually we speak in terms of average orbital radiuses, because we know that, you know, all orbits are a little bit elongated. That means that distance changes. So when we speak about r, we're usually talking about average radius. We're talking about the Earth around the sun, that'd be about 93 million miles. We're talking about the moon going around the Earth, that's around 250,000 miles, a little bit less than that. But you get the idea. So orbital radius r, small letter r is usually how we symbolize that, sometimes indicated with a letter d because it is a distance. So this, you know, this could be any unit of time. This usually in meters. You know, if it's, now we'll talk about the units a little bit later, but just kind of want to conceptually understand what each of those terms mean. Kepler's three laws, that was one of the very recent things we talked about, the little Ed puzzle on that as well. But Kepler's first law was the simplest of the one. It says basically the orbits of the planets are elliptical, not circular. And that was kind of a big mystery in science for a long time until Johannes Kepler came along. And he was actually a predecessor of Newton. They kind of overlapped a little bit, but Kepler kind of figured this out about the planets before we really had an understanding of what gravity is. He didn't really even know what gravity was. He just explained how the planets moved. So they are elliptical, and more specifically, they are elliptical with the sun at one focus. And focus means kind of like a focal point. If you want to remember how we talked about that, the two push pins and a marker example. You have a string and you draw that tight around two push pins. The further those push pins are apart, the more elliptical the shape that you can draw with it is. The closer the two push pins are to each other in the center, the more circular it becomes. Also remember that a circle is an ellipse. It's just an ellipse with an eccentricity of 0. An ellipse is not a circle, but objects can be a perfect circle. It's rare. There's always a little bit of ellipticalness there. And the term we use as a measurement for how elliptical something is, that we call that eccentricity. And again, just talking about elliptical orbits, some other terms we kind of threw out there was aphelion is when the Earth is furthest away, perihelion is when the Earth is closest in its orbit. This is, of course, a highly exaggerated drawing of the Earth's orbit. If we look at the Earth's orbit around the Sun, it's pretty nearly perfectly circular, but just ever so slightly elongated and elliptical. Kepler's second law, was the law of areas. We talked about that in the last video. An imaginary line from the sun to a planet will sweep out equal areas in equal amounts of time. I'm not going to go through explaining what that exactly means again. We should understand that from the last Ed puzzle. But I moreover want you to understand is what does it say about the speed of a planet as it relates to its orbital radius. That means that it has to mean that a planet is going faster when it's close to the sun and slower when it's further away. And again, if we go back to this elliptical orbit here, law of areas, just to get indication of that. But when you look at this picture here, again, any two equal areas, so if this is a planet around the sun, in 1 month it goes from here to here, in 1 month it goes from here to here. This blue area has to be equal to this blue area. And the only way that happens is the planet travels this large distance in 1 month, and this shorter distance in 1 month when it's far away. Which makes sense because orbiting objects are falling. And when do objects fall faster? When they're, I drop an object from the top of a tall building here on Earth. When is it traveling faster? When it's high above the Earth or when it's closest to the Earth? Same principle here, is it's falling and it's speeding up, and it falls around, and then it gets tossed back up, and it's slowing down, speeding back up. So then it zips right around, and slow, and then zips right back around. And again, this law of areas is a roundabout way of explaining roundabout way of explaining how this planet's speed changes, just the nature of how its speed changes with distance. Kepler's third law, this was the last one, this was the one that had an equation associated with it. It just related that the orbital period, of a planet to its orbital radius. So Kepler's third law said a few things. So orbital period increases with orbital radius. And how it increases is that the orbital period squared is related to the radius cubed. And that's, if you remember, on the Edpuzzle that we did, there was some examples we did with that, but it was the whole ratio. It compares to planets. Superscript and formats, text, superscript. There's my daughter laughing again. Enjoy her childish giggle. Hi, Izzy. Sorry, I had to find the superscript button there. Okay. So orbital period squared is related to orbital radius cubed. Sorry, I typed this. Orbital period increases the orbital radius. So the further away a planet is, the longer it takes to orbit the sun. That's not a surprise. Mercury takes like 89 days. Venus takes like 280 days. Earth 365 days. Mars is like a year and a half. Jupiter's 5 years, I believe. Saturn, Jupiter's 11 years, excuse me. Jupiter's 11 years, Saturn's like 30 years, and so on and so on. And so you get all the way up to Neptune, and Neptune takes a couple hundred years to orbit the sun. And that's how those things are related. Okay, so that is the first point that I want to make sure that we indicate here, is that orbital period increases with orbital radius, but also that for every orbital radius, there exists an orbital period. So we'll say assigned, for lack of a better word right now, is an assigned orbital period. Now, what does that mean? Okay, so that means that if a question I always like to ask is, what if there was another hypothetical planet? Let's call it planet X. Okay, and planet X is exactly as far away from the sun as the Earth is, 93 million miles away. But it's also exactly perfectly on the opposite side of the sun. Would we ever see that planet? No, we wouldn't. Because even if it was really, really big, say it was Jupiter's size, and it just happened to be at our exact same location, we would never see it, because it would always be exactly on the other side of the sun. And if it's exactly the same orbital radius, that means it would have to have exactly the same orbital period. So anything that is orbiting at Earth's distance would have to have an orbital period of 365 days. Everything that is, say, at the same radius as the moon from Earth would have an orbital period of 29 days. That's the orbital period of the moon, if you didn't know. Okay? And this is how we create things like, this isn't something we talked about, geosynchronous satellites, is that there's all different types of satellites, but these ones are kind of special. They stay above a fixed spot. And how is it they stay above a fixed spot on the Earth instead of going around it? Is because they are at a certain altitude where their orbital period is 24 hours. So they orbit at the exact same rate that Earth rotates. So in effect, they wind up staying at the exact same location above Earth at all times. But you can only have satellites like this at one specific altitude, because it has to have one specific orbital period, and that orbital period is the exact is 24 hours, the rotational period of the Earth. So that's how you create things like geosynchronous satellites. And GPS satellites are geosynchronous satellites, otherwise they wouldn't work. Okay, GPS satellites have to stay above fixed spots on Earth, and that's how they triangulate with each other and figure out where everything is and locate your phone or a GPS device of some sort, one way or the other. So these two key ideas here is kind of what I want you to get out of that. And the geosynchronous satellites were just kind of an example of that. Universal law of gravitation, understand conceptually the inverse square rule. I guess this isn't really a question, the proportions, but remember that the force of gravity is proportional to mass and is inversely proportional to the square of the distance between two objects. So it's proportional to both of masses. So that means you double the distance, the force of gravity is going to be 1/4 as much. You triple the distance, the force of gravity is going to be 1/9 as much. You make the distance 4 times as much, the force of gravity is going to be 1/16 as much. That's what an inverse square rule means. But to say that the force of gravity is proportional to the mass, say the mass of the Earth magically doubled. How would that change the force of gravity? It would double. What if your mass magically doubled and the Earth's mass stayed the same? Then the force of gravity acting on you would be the same. So there's that equation that we gave you here. There's the equation that we gave you between any two masses. So the force of gravity between any two masses, M1 and M2, typically you think this is like a planet, and this is some smaller object like a person or a ball, but this applies to any two masses. This could be big M for a planet, small m for a ball, a person, whatever. D is the distance between them, sometimes referred to as r, like you see in this equation. But between this and this, an inverse square relationship between this and this is a direct relationship. Remember that big G here, ironically, is a crazy, crazy small number. 6.67 times 10 to the negative 11. Universal law of gravitation, understand how to use the equation, enter values for any two objects, two planets, a planet and an object, two small objects, etc. Make sure that you guys can do that. So basically just make sure that you are able to use this equation here. If we jump over here really quick, let's see if I can do this with my hand. Nope. Oh, there we go. So here is our equation. G, we'll write it like this: big M to represent the planet, small m to represent the mass of the smaller object, and sometimes again either d or r squared at the bottom here. Okay, we need to know how do we use that. Remember that big G is this really small number, 6.67 times 10 to the negative 11. And remember that that means that in order for this number to become anything significant, One or both of these need to be really big because they're getting multiplied by this crazy small number, okay? So make sure you understand how to enter that in your calculator. Make sure you're only squaring the bottom of the equation. So let's say we solve this for my mass, roughly. I'm just going to do that because I kind of know the numbers off the top of my head. But let's say, what is the force of gravitational attraction between Mr. Schober and the Earth? You would plug this in like so. Let's say 6.67. To the negative 11th power times the mass of the Earth. That would be given to you. Mass of the Earth, about 5.98 times 10 to the 24th power. That E there, just like I wrote over here, means the same thing as times 10 to the... And then my mass is about 90 kilograms. We all have to put that over how far those two objects are away from each other. Again, this is the mass of Mr. Schober. Just say S for Mr. Schober. Here's the mass of the Earth. I'm on the Earth, so how the distance between us is 0? No, we need to talk about their distance between their centers. Now, that's about 6,400 kilometers is how far I am from the center of the Earth right now. That needs to be in meters, so that gives you 6,400,000 meters. Put that in scientific notation. That's 6.4 times 10 to the 6th power. And then that's getting squared. Okay, so again, this is the mass of the Earth here. This is the radius of the Earth, because we're talking about how far I am away from it. This is G, and this is just the mass of me. So all these values were given to you. The tricky part is, sometimes just with the scientific notation and the square and everything, it gets a little tricky. But try it really quick. Plug it in your calculator. This should come out to be roughly, it's a little bit less, but roughly 900 newtons. It'll be a little bit less than that, like 890 newtons or something like that. I forget the exact number off the top of my head. But if you get, 889 or 89 newtons, something very close to 900 newtons, you can be assured that you did it correctly. If you wind up with some wildly crazy high number or some wildly crazy low number, you know that you did not enter something correctly. Okay, so just something that you may want to practice doing. Won't be a ton of that, but I might give you a simple example where you have to do on quizzes or something like that. Again, I'm not going to make that quizzes test very, very challenging, but just something to give us to close out the week. All right, moving right along. Universal law of gravitation. Understand how to use the equation. Enter object for any two values. Two planets, a planet, and object. All right, I showed you guys that. Let's say shown on paper. All right, quickly, right along. Is the moon accelerating? Yes, it's in circular motion, so it has centripetal acceleration. Does that mean it's speeding up? No. What happens to an object that is placed at an altitude the International Space Station is at, and nothing else happens to it? Falls back to Earth, okay? It will fall back to Earth unless it's giving a appropriately high tangential speed to keep it in orbit. But again, as I keep saying, objects don't just magically float in space when you place there. Gravity exists in space and doesn't just magically shut off. It will fall back to Earth. Number 11, what is gravitational field strength and how does it change with distance? Gravitational field strength is just is an indicator of the strength of gravity at a certain location. Whereas all of us sitting on the surface of the Earth, we might have different weights, which means gravity is pulling on us differently, but that's a function of our own weight. But we are all experiencing the same strength of gravity. That is this, for our purposes, the same as the acceleration of gravity, that small g, same as acceleration of gravity. aka small g, which the gravitational field strength, otherwise known as the acceleration of gravity, equal to 9.8 meters per second squared on the surface of the Earth, or you could say 9.8 newtons per kilogram. In other words, 9.8 newtons of force will be pulling on you for every kilogram of mass that you have. And second part of that question, how does it change with distance? It also follows an inverse square rule. Okay? If the, twice as far away, it'll be 1/4 as much. So if, say, at the surface of the Earth, so right now we're 4,000 miles away. That's equal to 6,400 kilometers. At 4,000 miles away, it's equal to 9.8 meters per second squared. So what must it be at 8,000 miles away from the center of the Earth? That means, like, if we go 4,000 miles above where we are right now, it would be 1/4 as much, which 1/4 of that is about 2.45 meters per second squared, or means the same thing as newtons per kilogram. Same thing here. Again, meters per second squared and newtons per kilogram is really the same unit if you play around with what a newton means. Is there gravity in space? Yes, of course. Don't be crazy and think that there is not. That is how objects orbit, and really that is how the entire solar system, and moreover how the entire universe is held together. To avoid friction with the atmosphere is why satellites have to be launched above the atmosphere. Okay? Satellites, to be in orbit, need to maintain a really, really high speed. And if they're interacting with the atmosphere, if the atmosphere is slowing them down, we obviously cannot expect to be staying in orbit. So that is the only reason. It has nothing to do with gravity being weaker above the atmosphere. It just has to be, we have to be in a frictionless environment. Otherwise, you're just going to have to be using rockets continuously, which is, kind of an untenable situation. Number 14 here. Does the speed something needs to have at a certain altitude in order to be in orbit depend on the mass of the object? It's a tricky one. No, you would think it doesn't. Okay? And we know that because equation for orbital speed does not have mass in it. Okay, if you remember, we got that equation by saying the centripetal force is equal to the force of gravity. You plugged in both of those equations, mvt squared over r for this, and g m1 m2 over r squared. You solve those equations for orbital speed. You solve those equations for orbital speed, and you get this guy. Orbital speed is equal to square root of big G times the mass of the center object divided by r. So this is the m of the Earth, if we're talking about orbiting the Earth. The small m's, the mass of the orbiting object, wind up canceling out. So that tells us, this is actually a pretty simple equation. So if I would need to find the speed that the International Space Station need to be orbiting at, I would just be square root of big G, 6.67 times 10 to the negative 11th, times the mass of the Earth, divided by how far away that is. It's like 250 miles or so. I don't know what that is in meters. But yeah, whether it's a small object or a large object, the mass of the object does not matter. The mass of the center object is the only thing that matters, as well as how far you are away. Now, if you, again, look at that equation, just copy that over here. If you look at that equation, like I said, it's pretty simple, and you see the radius here. You can simply see that with increased radius, well, that's weird. Try that one more time, paste. With increased radius, the speed required is going to be less. Okay, so something orbiting close to Earth has to be going faster than something much, much further away from Earth. So in other words, say the International Space Station has to have a much higher orbital speed than the Moon does, because the Moon is a lot further away. It's like, what, 100 times further away. Is 1,000 times further away? No. But it's a lot further away, and so it's the moon's orbital speed certainly is a lot less than that of the International Space Station, which is in a low orbit. I've done this before. I'm not going to bother taking up your time by doing this now, but remember the orbital speed equation. It just starts with centripetal force is equal to Fg. I brought that up before, but just mvt squared over r is equal to g, big M times small m over r squared. You wind up with this equation. Okay. Again, you can look back in your notes and see that. You don't need to show me that on a test, of course, but I just want you to understand that this equation comes from that relationship. And it's really the same relationship as saying centripetal acceleration is equal to the acceleration of gravity. Both of those are saying the exact same thing. All right, moving right along. The Earth's radius is 4,000 miles. What would the acceleration be of gravity at an altitude of 4,000 miles? So in other words, we double the distance, which means the acceleration of gravity will be 1/4 as much. 9.8 times 1/4, or divided by 4 would mean the same thing, would be 2.45 meters per second squared. What would be the centripetal acceleration of an object in orbit at an altitude of 4,000 miles? That's asking the exact same question. That's why I put that there, because those two things may not seem like it, but it's asking the exact same question, because the centripetal acceleration of an orbiting object is equal to the acceleration of gravity at that altitude. All right, if an object weighs 1,000 newtons on the Earth's surface, will it weigh at an altitude of 8,000 miles? Okay, so in other words, we have tripled our distance now, because we're right now at a distance of 4,000 miles, and then we go 8,000 more. So that means we went from being 4,000 miles away from the center of the Earth to 12,000 miles away from the center of the Earth. And that means that we tripled the distance, which means that the force of gravity should be 1/9 as much via the inverse square rule. So 1/9 of 1,000 is about 111 newtons. Okay, so again, just apply the inverse square rule there. Triple the distance. I know it may not be obvious right away why this means tripling the distance, but remember that we right now are 4,000 miles away from the center of the Earth. If we then go to an altitude of 8,000 miles, our total distance from the center of the Earth now went from 4 to 12, which means we tripled the distance, which means the force changes by a factor of 1/9. That's how the inverse square rules. All right, number 19 here, it says, what is the force of gravity between a 90-kilogram man and a 90-kilogram woman that are 2 meters apart? And again, that's just using that force of gravity equation again, where you should wind up just being able to use, this guy. Force of gravity is equal to m, big M, small m, over r squared. Now, in this case, big M represents the mass of the Earth. Excuse me. I'm going to get my problems mixed up here. Try this again. So Fg is equal to big G. Then we'll call it M1 and M2 instead of big M and little m, since the Earth isn't a factor here. And R squared, or D squared, between them. Okay, so just plug these numbers into your calculator. 6.67 times 10 to the negative 11th. One person has a mass of 90. One person has a mass of 60. The distance between them was, I forget how much. Let me look back here. Distance between them was 2 meters. So 2 meters squared, so just 2 squared, so 4 on the bottom. Be careful how you enter that in your calculator. And you do all that, you should wind up with a very low number, 9.0 times 10 to the -8th newtons. So that's just two people standing a couple meters apart. A calculable force, but an incredibly small one. Obviously, a negligible force between the two. But we can just be able to use Newton's law of universal gravitation here, whether we're talking about two people or the force of gravity between the Earth and a person, like in the other example I gave you before. All right, so our answer there was, what did we say, 9.0 times 10 to the -8th newtons. So just double check that you can find an answer there. For an orbiting object, what force is providing the necessary centripetal force? Of course, gravity is the answer there. If an object has the same orbital radius as Earth, what would its orbital period have to be? Have to be the same. With every orbital radius becomes a known orbital period. So 365 days, 1 year, however you want to express it. Same orbital radius means same orbital period. Cardiad asked this, but does the mass of an orbiting object affect orbital speed at all? No. At any orbital radius, the same orbital speed is required, whether you're talking about a baseball, a person, a spaceship, or an asteroid, a planet, whatever else. What happens to orbital period as you increase orbital radius? Orbital period increases, like I said. Mars and Venus, planets that are close to us, they have a shorter orbital period. It takes them less time to orbit the sun. Planets that are further away, Mars, Jupiter, Saturn, take a further amount of time. Mars takes a year and a half. Jupiter is like 11 years. Saturn is 30 years, and so on and so on. With increased orbital radius is also increased orbital period by that squared cube rule. What happens to orbital speed as you increase orbital radius? Orbital speed decreases as we increase orbital radius. Already covered that. How do you understand how to use the inverse square rule of gravity? Both the force of gravity and the acceleration of gravity follow an inverse square rule. So remember what an inverse means. Inverse means flip a number, then you square it. So if distance doubles, so distance is 2 times as much. Maybe go over to our drawing board here really quick. If distance here is 2 times as much, the inverse square of that number 2 is by what happens to the force of gravity. So the force of gravity is 1/4 as much. If distance is 3 times as much, the force of gravity has to be 1/9 as much. Say if we take that, say distance becomes 6 times greater. That means that the force of gravity is going to be 1/36 as much. Okay, so that's what that means, is that the force of gravity is proportional to the inverse. Inverse means 1 over, and then you square it. Okay, so the force of gravity, that symbol means proportional to. Force of gravity proportional to 1 over the distance squared. So by whatever factor the distance changes, the inverse square of that is what happens to the force of gravity. I may have said that wrong just now, but whatever happens to the distance, the inverse square of that number is what happens to the force of gravity. The inverse square of 2 is 1/4. The inverse square of 3 is 1/9. The inverse square of 6 is 1/36. If this was 10 times as much, the force of gravity would be 1/100th as much. Okay, so that's what that inverse square rule means. Make sure we understand that. So explain that on the other one. Escape speed, I didn't talk about that, and I'm not going to now, so just kind of omit that. But basically means every planet, every body in space has a certain speed that you could leave and you never come back. It's the speed with which you can escape. For the Earth, it's about 7 miles per second. So if we launch something up from the surface of the Earth at 7 miles per second, it would never get pulled back. It would just keep it floating out into space forever and ever. Earth's gravity would never pull it back. All right. Again, probably won't be quizzed over that because I didn't really talk about it, but that's what it means. It is a good term to know when you're talking about gravity. Are astronauts in orbits? You see them weightless. They're floating around. They're totally weightless. Are they floating or falling? They are falling. They're not floating. They're in a continuous free fall, and that is why they feel weightless. They are, of course, not actually weightless. How is gravitational strength, field strength, different than gravitational force? Okay. Gravitational field strength, GFS for short, is strength of gravity at a certain location. Gravitational force, adversely, is how strong gravity is pulling on a certain object. Okay, so this is the same for everybody at a certain location, but this is different for each individual person or object at a certain location. Would be an easy way to explain that. Are astronauts in orbit around the Earth? You see them floating around. Are they actually weightless? No, they are not. Why do they feel weightless? You'd say that is because they are in a continuous free fall. And why does that make them feel weightless? Is because they have no support force acting on them. Okay, you take away that support force, you feel weightless, right? Just if you jump off the side of the building the whole time you're falling back to Earth, you feel weightless then, because nothing is supporting you. Okay, so because they're in a free fall, we feel a weight because of the support force, not because of gravity itself. Okay, so you take away that support force, yeah, you're gonna feel weightless. But that, of course, does not mean that gravity has stopped acting on you. There's not really anywhere in the world where gravity anywhere in the universe really where gravity is like not acting on you at all. Gravity is pervasive, extends throughout the universe. What would happen to a person's weight if they went to the moon? It would reduce because the gravitational field strength, G, is less. G on the moon is about like 1/6 of the Earth's. Okay, so you would weigh less on the moon. I think the next question, or no question, I'll add this here, is 31. What would happen to your mass if you went to the moon? And the answer there is, of course, nothing. Mass has nothing to do with gravity. Mass is how much matter is in an object. That's not going to change. That has nothing to do with the pull. That is a factor of like how many atoms and what elements and stuff you're made out of. Okay, so mass is not dependent on gravity, but weight is. Weight and force of gravity, that's an important idea too, is weight and force of gravity are synonymous terms. So kind of a long video here. Like I said, I'm not going to put it in an Edpuzzle or anything. Just going to be a YouTube video so you can skim through it, review as needed. I'll also post this document for you to kind of fill in as you go along. So it should be a good little review. But between this and short little quizzes, that'll be about it for the week. And you enjoy your spring break.